Okay, this video series is a remake of one I did previously in a different channel, and I wanted to redo it because this format is a little bit more visually appealing, and I also have a new microphone, so the audio quality as well will be substantially better. So let's get started. For people who haven't seen the previous videos, this is clearly about extremely large numbers. So what is an extremely large number? Well, this really depends on your level of mathematics. Let's say you're in elementary school and someone were to ask you what's a really large number that you can name. Well, you might know some basic numbers like 10, let's say, and you know the operation of addition. So you just start adding tens together. You go 10 plus 10 plus 10 plus 10, and let's say you put 10 of them down on the paper. You can get to 100 in this way. So that might seem like a pretty big number when you're in elementary school, but you quickly realize that you can keep on adding tens. You can add tens until the cows come home, and the exercise quickly becomes arbitrary. Then you learn something called multiplication. Now with multiplication, we can do the exact same thing. We could add 10 tens together, but in only one operation and get to the same result. We can then go further. Let's say we have 10 times 10 times 10 times 10 times 10, and we do that 10 times. Well, we can reach something like 10 billion. 1, 2, 3, 4, 5, 6. So a very large number, something that would be almost impossible to do with simple addition. And the same thing happens, though. We realize that we can keep on multiplying things together, and it becomes arbitrary at some point when this writing down operation becomes untenable. We move on to the next part now, like you might learn something like this in high school, exponents. And we can write down this 10 tens multiplied together as simply as this, just 10 to the power of 10. And this is also equal to 10 billion. Now, this is kind of where it ends for most people. The last operation people usually learn about as far as constructing large numbers is exponents. And there's a reason for that. Exponents pretty much get us to any useful number that we would ever need. Take, for instance, numbers that most people deal with every day would be on the order of billions and trillions, perhaps. There's 7 billion people in the world, roughly. And even trillions, because the number of money that's flowing around the world and stuff like that is on the order of trillions, so we can write that down. We'll just do it in exponent form here, 10 to the 12. If you're into cosmology, you might be used to dealing with even larger numbers. So let's say the mass of the Earth, for instance. Mass of Earth is roughly 10 to the 27 kilograms, which is substantially larger than either of these numbers. And even something like this, the number of particles in the entire universe is around 10 to the 80. And if you're really out there, you might have learned some things about permutations and whatnot. And just to give you a really extreme example, let's say you take all of the quantum spaces in the entire universe and you take all the permutations of that. So that's similar to like the number of possible universes. This is a very, very large number, and it's this thing is screwing up on me here. There we go. Is approximately 10 to the 10 to the 183. So if you know the name for a googolplex, which is 10 to the 10 to the 100, this is larger than a googolplex. So it's a very, very, very large number, and it's pretty much at the limit of anything that we need to use in any kind of science or whatever. And it can still be reached with exponents, though. So it's kind of the usefulness of the numbers that limits what operations we learn about. But there's really nothing stopping us from going further. And I want to kind of talk to you about the philosophy of extremely large numbers, because pretty soon we're going to get past all this. We're going to get past numbers that are actually useful for anything. And people think, well, what's the point then? It kind of becomes arbitrary, because you can always add one. You can always make new numbers. There is no limit. There's no such thing as saying like what's the highest finite number. And I want to kind of get people out of this mindset, because the reason for coming up with extremely large numbers isn't their usefulness. It's developing stronger and stronger mathematics to create these numbers. So in the same way that we weren't satisfied with simply adding, we created multiplication, and we weren't satisfied with that, we can create exponentiation. We can keep on going with this idea of creating stronger and stronger mathematical concepts. So I'm going to show you an error that most people do when creating large numbers. So let's say you know about all these concepts, addition, multiplication, exponentiation, And you want to go on for this. I asked somebody, let's say I asked somebody who's well-versed in all of these, what's the biggest number you can come up with? They might do something like this. They say, oh, let's take a Googleplex times 10 to the power of 50 plus a million. And they just start jamming all these concepts together, these numbers. And this is something that's called a salad number. Because it looks like salad. It looks like you just jumbled a bunch of stuff together in some kind of haphazard way. And this really is an arbitrary way of making large numbers, in that it's pretty much totally useless. Whatever. If you don't know a whole lot about constructing large numbers, you realize that these factors here really do nothing to this number at all, because this number is substantially bigger. Whatever. So in order to make large numbers, we really need a formal mathematical system to reach them. We can't just start jamming things together. And that's what I'm going to show you how to do. I'm going to show you how to put things together in a rational way, in something that's mathematically stronger, not just haphazard. So for starters, let's continue on where we left off. We described multiplication as repeated addition. So let's say we have 10 plus 10 plus 10, and we do that 10 times. This is the same as saying 10 times 10. Now let's take 10 times 10 times 10 times 10 times 10 and do this 10 times. Well, this is the same as 10 to the power of 10. So it's kind of a recursion type of thing. We take 10 tens and add them together to define multiplication. We take 10 tens and multiply them together to create exponents. Well, let's just continue in this trend. There's nothing stopping us from going further. Let's say we have 10 to the power of 10 to the power of 10 to the power of 10, blah, 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 blah. Well, there's actually a name for this. It's called tetration, and it's denoted 10 with the 10 on the left-hand side. And this means 10 tens stacked together in a tower. And you can go on with a recursive tetration. That's called pentation. And this keeps on going and going and going and going. And you can create formal mathematical operations that get you to numbers far, far larger than you could ever just jam together, just knowing addition, multiplication, and exponentiation. So before we go any further, I want to explain some of the peculiar properties of exponents, because this is going to be very, very important as we move on. So that's going to be in the next video.